Good morning. Today, we are going to study thermodynamics. Now I know the moment people hear that word, they start imagining long equations, complicated diagrams, and professors writing mysterious symbols on the board. But today I want you to forget all that. Instead, I want you to imagine a kitchen. Yes, a kitchen. Because a kitchen is actually one of the best laboratories for understanding thermodynamics. Every time you boil water, fry an egg, bake bread, or use a pressure cooker, you are performing a small physics experiment. The funny thing is, cooks often understand thermodynamics intuitively, even if they've never heard the word. So let's play a little game. Imagine we are not physicists today. We are curious cooks trying to understand what the universe is doing while we prepare dinner. 1. Boiling water. The dance of molecules. Let's begin with something very simple: boiling water. You put a pot of water on the stove. You turn on the flame. After a while, bubbles appear. Now here is the question. Where do those bubbles come from? Many people say, well, the heat makes the water boil. But that's not really an explanation. That's just repeating the observation. What's actually happening is something far more interesting. Water is made of tiny molecules, little things moving around constantly. Even when the water is cold, those molecules are moving. They are bouncing, colliding, and sliding past each other like a crowded dance floor. When you turn on the stove, you are adding energy to these molecules. That energy makes them move faster. Faster motion means stronger collisions. Eventually, some molecules move so fast that they escape the liquid and become gas. And when many of them escape together, they form those bubbles we see. So boiling water is really just a crowd of molecules saying, "That's it. I'm leaving the party." And the temperature at which this mass escape happens, for water at normal pressure, is 100 degrees C. But here's a curious thing. Once water reaches 100 degrees C, it doesn't get hotter, even if you keep heating it. Isn't that strange? You keep pumping energy into it, but the temperature stays the same. Where does the energy go? It goes into breaking the bonds between molecules, allowing them to escape as steam. So boiling water is not about increasing temperature anymore. It's about changing the state of matter. That's thermodynamics at work. 2. Heat transfer. How energy travels in the kitchen. Now let's talk about how heat actually moves. Because heat is a little bit like gossip. It spreads everywhere. In physics we say there are 3 ways heat can travel. 1. Conduction. 2. Convection. 3. Radiation. And the beautiful thing is, you can see all 3 inside your kitchen. 3. Conduction. Passing energy hand to hand. Imagine frying an egg in a pan. You put the pan on the stove. The flame heats the metal pan. Then the pan heats the egg. But how? The metal atoms in the pan start vibrating faster as they gain energy. Those vibrations bump into neighboring atoms, which bump into others, and the energy slowly moves through the material. It's like people standing in a line passing a ball. One person pushes the next, who pushes the next, and the motion spreads. This is called conduction. Heat moving through direct contact. Metals are very good at this because their electrons move freely and carry energy efficiently. That's why a metal spoon in hot soup quickly becomes too hot to hold. The heat traveled through the spoon right into your hand, which is physics reminding you, maybe use a wooden spoon next time. 4. Convection. The great circulation. Now, let's go back to our boiling pot of water. Something else interesting is happening. The water at the bottom of the pot gets heated first. Hot water becomes less dense, which means it rises. Cooler water sinks down to take its place. So the water begins to circulate in little currents. Hot water up, cool water down, up and down, round and round. This motion is called convection. It's the reason soup heats evenly in a pot. It's also the same mechanism that drives ocean currents, weather systems, thunderstorms. So when you stir your soup, you're actually helping a process that nature already started. Cooking, in a sense, is controlled weather inside a pot. 5. Radiation. Heat that travels through empty space. Now suppose you put bread into an oven. You might think the hot air cooks it. But actually, much of the cooking comes from radiation. Hot surfaces inside the oven emit infrared radiation. These are electromagnetic waves, cousins of visible light, carrying energy. They travel through the air and get absorbed by the food. That energy makes the molecules in the bread vibrate faster, raising its temperature. In other words, your bread is literally being bathed in invisible light. The same process warms your face when you stand near a campfire. Even if the air is cold, the radiation still reaches you. So radiation is heat that doesn't need matter to travel. It can cross empty space, which is exactly how sunlight warms the earth, and also how an oven browns your pizza. 6. Frying. A violent thermodynamic event. Now frying is particularly interesting. When you drop food into hot oil, something dramatic happens. Oil can reach temperatures around 180 degrees C, much hotter than boiling water. When water inside the food touches that oil, it instantly turns into steam. Steam expands about 1/700 times its liquid volume, so tiny explosions occur at the surface of the food. That's the sizzling sound you hear. It's basically thousands of miniature steam explosions. These explosions push oil away from the surface and create the crispy texture we love. So the next time you fry something, remember, you're listening to thermodynamics popping like fireworks. 7. The pressure cooker. Playing with boiling point. Now let's look at a wonderful invention. The pressure cooker. Normally water boils at 100 degrees C, but that temperature depends on pressure. At higher pressure, molecules find it harder to escape the liquid, so they need more energy to boil. Inside a pressure cooker, steam cannot escape easily. Pressure builds up, and the boiling point of water rises to about 120 degrees C. Now food cooks faster because everything is hotter. Beans soften quicker. Meat becomes tender faster. So a pressure cooker is really just a clever way of telling water, you're not allowed to boil yet. And because the water cannot boil, it keeps getting hotter, which speeds up the chemistry of cooking. 8. Baking. A beautiful symphony of physics. Baking bread is one of the most elegant examples of thermodynamics. Inside bread dough are tiny pockets of gas produced by yeast. As the dough heats, several things happen. 1. The gases expand. 2. Water turns into steam. 3. Proteins in the flour solidify. These processes inflate the bread like a balloon, while simultaneously setting its structure. That's why bread rises in the oven. Meanwhile, the outer crust gets hotter and undergoes something called the Maillard reaction. This reaction creates hundreds of new flavor molecules and the brown color we associate with baked bread. So baking is not just heating food, it is a chemical orchestra, with temperature controlling every instrument. 9. Entropy. The universe likes messy kitchens. Now we come to a very famous idea in thermodynamics: entropy. Entropy is often described as disorder, but let me give you a kitchen example. Imagine a perfectly neat kitchen. Everything is organized, spices lined up, utensils arranged. Now start cooking. Within minutes, the flour spills, spoons move everywhere, the bowls pile up, the crumbs appear. Order naturally turns into disorder. But the reverse, spontaneous cleaning, never happens. You never walk into the kitchen and see the dishes washing themselves. Why? Because the universe prefers states with more possible arrangements. A messy kitchen has far more possible configurations than a perfectly organized one. So the second law of thermodynamics tells us that entropy tends to increase. Cooking obeys this rule perfectly. The more delicious the meal, the more chaotic the kitchen afterward. So entropy is basically the universe saying, tidiness requires effort. A 10. Why food tastes better when hot? Now here's a curious question. Why does hot food taste better? Thermodynamics again. Heat increases molecular motion. When food is hot, aroma molecules escape more easily into the air. These molecules reach your nose, activating smell receptors. Since much of taste actually comes from smell, hot food appears more flavorful. Cold pizza has fewer escaping molecules. Hot pizza launches a flavor cloud directly toward your nose, which is why reheated pizza often tastes better than cold pizza. Physics improves dinner. 11. Curiosity in the kitchen. The beautiful thing about physics is that it hides in ordinary life. You don't need a giant laboratory. You only need curiosity. Every pot of boiling water is a molecular drama. Every frying pan is a heat transfer experiment. Every oven is a radiation chamber. And every messy kitchen is proof of the second law of thermodynamics. So the next time you're cooking, don't just follow the recipe. Ask questions. Why does the water boil? Why does the bread rise? Why does frying make things crispy? Physics begins the moment you become curious. And if you think about it long enough, you start to realize something wonderful. The laws that govern stars and galaxies are the same laws that govern your kitchen stove. Which means that every time you cook dinner, you are participating in the thermodynamics of the universe. And that, I think, is a pretty delightful thought. Now, before we finish, does anyone here feel hungry? Because after talking about thermodynamics for this long, I certainly do.